Today we're gonna start talking about simplification of Boolean expression. Remind you about the topics that we covered last lecture. So we start about talking Boolean expression, introducing different logic gates, and talking about different theorem in digital logic that you can use to simplify Boolean expression. The table that we draw different theorems, and very important law which is called De Morgan's law. It had two theorems. One was related to NAND, which also called bubbled OR, which it gives you a, so this is NAND gate. It can be written as A prime plus B prime. So you can complement two inputs and then or the input. So that's one of the theorem for De Morgan's law. And we had the second theorem for De Morgan's law, which related to NOR gate. So this is a NOR gate and can be written as A prime and B prime. So try to memorize these two theorems, because in the future if you go to a job interview, sometimes they ask for De Morgan's law. Okay, try to understand it very well and memorize it. So now let's start today's topic. We want to see how to simplify the Boolean function. There are different techniques. One is just algebraic method. Another one is K-map method. The other one is Queen method, McCluskey, and then is variable intermapping. So in this course, we covered the first two, algebraic method and K-map method. Today we start the first one, which is algebraic method. Let's start the first technique to simplify Boolean function. So algebraic method. So in algebraic method, you have two types of method. One is sum of products, which in short it's SOP, and the other one is product of sum, POS. In the future, you're working at a company, you have a circuit, your boss asks you, okay, what's the function of this circuit? What does it do? So first you have to figure out, okay, what's going to be the output for the different combination of the inputs. That's basically just drawing the truth table. So the first step to find the functionality of the circuit is draw the truth table. So as we saw before, just you draw the truth table, you put the inputs on the left side of the table and then the output on the right side. So let's say you have a circuit, it has three inputs, and then you have output F. Then you try different input and get your output. So the first try is 0, 0, 0. You get 0 for all the inputs. Let's say you get 0 for the output. And you try all the combination 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Since you have three inputs, as I mentioned before, so since you have number of inputs Number of inputs, it's 3. So the number of rows in your truth table is going to be 2 to the power of 3, which is 8. So you're going to have 8 rows in your truth table. So now first we want to discuss the sum of the product, SOP. Okay. For sum of the product, let's say you have output for this circuit and you get, let me write down the output for this circuit. So the second one is 1 0 1 0, and then the last 3 is 1. So let's say you want to try find the functionality, find the Boolean expression of your circuit using sum of the product, SOP. What you can do is basically you have to focus on the rows of your truth table that the output is 1. So it means that this row, and the last 3 rows. So for SOP, you just look at the rows that the output is 1. Okay. And then you write down the expression for each of these rows. Okay. So when you're writing SOP, these rows is going to call min terms. So these are, each of these rows is min term. Okay. So min term. So the first one is M0, M1, M2, M3, 4, 5, M6, and M7. So these are min terms. So for SOP, you use these min terms. So you write down the function f based on these min terms. So you're going to use min terms 1, min terms 3, min terms 5, 6, and 7, which the output is 1. The output is 1 for these cases. So now how to write it? So the first one, let's look at the, let me write it 1. So the first one, as I said, since the output is 1 for SOP, for the inputs that get 0, you put prime, the complement of the input. So it means that X is going to be prime. Y, since Y is 0, you get prime of Y. Then Z is 1. So since Z is 1, you just write down the Z without any prime, without any complement. So that's the first term for your SOP. Then you add this to your second term, which is the fourth row. So you're going to get X prime, Y, and Z. Plus, this is second. The third one is X, Y prime, Z. Then for the fourth, you get X, Y, Z prime, and the last one is just X, Y, and Z. So that's going to be your SOP. So why SOP? Why sum of products? Why we call it sum of the products is basically because you are summing, you're adding the terms that is going to be product of each other. That's sum of the products. So basically you are ORing and the terms. If you want to write it in digital board, so you sum of the product is basically you are ORing. So these are OR function. So you are ORing the ANDed terms. So that's sum of the product. But this is not, oops, sorry. This is not a simplified version, okay? So this is called canonical form. Canonical form, it means that each of the terms have all the variables, all the inputs in. So if you look at all the terms, you can see all the inputs in all the terms. So that's why it's called canonical form. Canonical form is not minimal form. For this function f, which was x prime y prime z, x prime y z plus x y prime z plus x y z prime plus x y z. So as I said, this is canonical form. It's not minimal forms. So for all these four, you can, and this one, you can just factorize z. So you get x prime y prime plus x prime y plus x y prime plus xy. So I factorize z from all these terms, and then we have x, y, z prime. And then you can see that from these two, you can just factorize y prime. You get y prime x plus x prime. And for these two, you factorize y, you get x prime plus x. And basically you get x prime x, y prime y multiplied by z plus x, y, z prime. X prime plus x is just 1. Y prime plus y, every variable or function by its complement is going to give you 1 at the output. Okay, so you're going to get 1 for these two. 1 multiplied by 1 also is 1, so you get the answer is z. So this is going to be 1. So z plus x, y, z prime. And we had another theorem which we discussed last lecture. It was if we have x plus the complement of x plus multiplied by something, then you're going to get x plus y. So here you have z prime from this. So you can get z plus x, y. So that's the minimal form. From canonical form, we get to minimal form. We talk about SOP. SOP. As we said, we are just adding the ANDed or multiplication terms. Okay? So, and we work with min terms. Sometimes they show the SOP as something like this. So they put the addition and they put m as a min term, and it's going to be like 2, 4, 6. This means that if you have a truth table, x, y, z, and min terms of m0, m1, m2 to m7, then you have, when you say m2, it means that this row is going to have the output 1. Let me m3, m4. Then this row is going to have an output 1. And also m6 is going to have an output 1. So that's another way to show SOP. You put the summation, that's the sum of the product of these min terms. So now I want you to write down the min terms or the SOP based on what I wrote here. Write down the Boolean function and then simplify it. You don't need to draw the truth table to write down the SOP. You can find it from this here. So 2 is 0, 1, 0. So in binary. Then since this is SOP, if it's 0, the input is 0, it's get prime. So it's get x prime, y, and then z prime. Then 4 is 1, 0, 0. So you get x, y prime, z prime. And then 6 is just 1, 1, 0. So you get x, y, and z prime. So you don't need to draw the truth table. You just write down the binary representation of the min terms and then change it to your variables. And you get prime if it's 0. You don't get prime when it's 1. So if you want to simplify, what you can do, the first one, we just write it down. The second one, I'm going to factorize x, z prime. I get y plus y prime. And as we explained, y plus y prime is just 1. Then I get z prime factorized from these two terms. I get x prime y plus x. And again, as we explained, if you have x plus x prime something, that x prime can be removed. So you get z prime multiplied by y plus x. So now we want to see how build a circuit from SOP. So let's say you have this SOP. And when you want to implement, basically you get x, y, y prime, z, and it, and then you have x prime, y prime, z, and then you have the last one is x, y prime, z. Okay, so and this, and then you get the OR function, the OR gate, and then you get the output. Okay, so that's why the implementation of SOP is called AND OR. And or two level, it's a 2-level implementation. Because you have the AND gates first, all these AND gates, and then you have OR gates. So it's called AND OR implementation. That's for SOP. So let's now talk about POS. POS, which is product. The second method, product of sum. So it's POS. So basically, ANDing or terms. That's POS. So how we write down the POS. Let's say again you have a circuit, you want to find the functionality. You draw the truth table. So let's say these are your inputs: 0, 1, 2, 3, 4, 5, 6, and 7. These are the inputs. And then the output is going to be 1, 0, 1, 0, 1, 0, 1, 1, 1. Now you want to find out the product of sum. For product of sum, you use max terms. So max terms. Max terms are shown by capital M. M0, M1. So each of row is one max term. M2, M3, 4, 5, 6, and M7. So these are the max terms. For product of sum, you choose the rows or max terms that the output is 0. Like this row or this max term, M0, M2, M4. So you write down product of sum based on these terms. 1, 2, and 3 terms. So the first term, for product of sum, you're gonna have the multiplication between the parentheses. So how many terms? We have 3 terms. So this is basically M0, this is your M2, and this is your M4. So the multiplication or AND is going to be between the parentheses. And then you have OR inside of the parentheses. Now you put the inputs X, Y, and Z. Here, since we are writing F for when the output is 0, we are considering when the output is 0. Then if the input is 0, we don't complement. So X, for example, for the first term, X is 0, we don't complement. You put X. Y is 0, you don't complement. And then Z, you don't complement. Then for the second term, X is 0, you don't complement. But since Y is 1, then you complement Y. Y prime. X, Y prime, and then Z. And the last one, it's 1, 0, 0. 1, 0, 0. Since the first one is 1, you don't, you complement, and then you get Y and Z. So that's how you write the product of sum. The simplified version of this is going to be, you can try it at home to see if you can get this result. Okay, so this is canonical form, and that's the minimal form. So this is the POS. So to summarize, we had 2 methods. One was SOP, the sum of products, and the other one was POS. The sum of the product was just you put the multiplication inside of the parentheses and addition outside. But for POS, you put addition inside of parentheses and multiplication outside. So for sum of the product, you write down the Boolean function for when the output is 1. For POS, you write it down when the output is 0. For the SOP, if the input is going to be 1, you just write down the name of the input. If it's 0, you complement that and write it down. And POS, if you have X is 0, it doesn't get a complement. If it's X is 1, the input is 1, you complement that. So that's how you write down the canonical form from the truth table and write it down the Boolean function. And if you implement the POS, you're gonna have the ORs, and then you're gonna get the AND. So this is OR and implementation. As the SOP was AND OR. So it was AND OR. So this is SOP is AND OR, POS is OR AND. So now let's say you have a Boolean expression and you want to convert it to canonical form or SOP or POS. How we can do that? So let's first discuss the conversion to SOP. So let's say you have F is going to be XY plus XZ prime plus YZ. So this is not canonical form. Now how to convert it to SOP? You just look at the terms and see that what is the input that is missing in that term. For example, for XY, it's missing Z. For the second one, it's missing Y. And for last one is missing X. Okay, so the first step is finding the missing variable or input in each of terms. The second step is AND each term with missing literal plus its complement. So you're gonna have your F X Y, then you're gonna AND with the missing variable. So the missing variable is Z plus Z prime. The missing variable plus its complement. Then you have the second term XZ prime Y plus Y prime plus YZ X plus X prime. And then you multiply. You get XYZ XYZ prime XYZ prime XY prime Z prime XYZ X prime YZ. So this is going to be your SOP. And then you can see that these two are just repeated based on the theorem that it said X plus X is just X. We use this theorem. You just write down one of them. You don't need to write both. And then this is the same. So you write down just X, Y, Z, one of the term. X, Y, Z prime, X, Y prime, Z prime, plus X prime, Y, Z. and this is going to be your SOP. So now the conversion to POS. Okay, the first step was finding the missing literals, and then the second step is OR each term with missing literals, multiply or ANDing with its complement. So let's say you have this F first. You find out the missing term, so it's Z here, this is Y, and this is X. So you write down X plus Y, and then you OR with the missing literal multiplied by its complement, Z multiplied by Z prime. X plus Z, and then you get Y prime. And last one is Y plus Z prime multiplied by X prime. So if you multiply, you get X plus Y plus Z, X plus Y plus Z prime, X plus Y plus Z, X plus Y prime plus Z, X plus Y plus Z prime, and X prime plus Y plus Z prime. So you get these terms, but some of them are just repetition. So like this term is repetition of this term, so you just write down one of them, and this one is repetition of this. So these are repetition of each other, so you just write down one of them. So X plus Y plus Z, X plus Y plus Z prime, X plus Y prime plus Z, and X prime plus Y plus Z prime. So that's how you convert that function F to the POS. And then from here you can draw the truth table. These are the max terms, yeah? So this is 0, 0, 0. Since the POS is written when F is 0, so if it's the variable, you get 0. So this is M0. So this is 0, 0, 1. So you get M1. You get 0, 1, 0. So this is M2. And then you get 1, 0, 1, which is M5. So that's how you write the POS. So your POS is going to be product of the max term of 0, 2, 2, and 5. So for POS, you write down this symbol, which is a product symbol. and then you write down the max term. You write down it with the capital M. So in SOP, you show it by something like that. F is summation of min terms, which is a lowercase m. So let's say 0, 1, 2. But for POS, you will write it down. F is product of max term, capital M, 0, 1, 2, 3, for example. So this is how you write it down in short expression. For SOP and POS is like this.